So, what are the goals of this course? I'd say that the broad goals of this course are the following three. The first one is that I'd like you to gain an understanding of systems in an abstract way. And the reason why I'd like you to understand systems in this more abstract way is that then you can apply all the knowledge that you gain in this course to a very wide variety of systems, because all the principles that we are going to see in this course are applicable to systems that are very, very heterogeneous in nature, that can be applied to systems that are technological systems, they can apply to biological systems, they could apply to chemical systems, mechanical systems, even financial systems. So all the knowledge that you obtain from this course, even though it's a course about fundamental topics in automatic control, is going to be applicable to a wide variety of cases, and so I want you to understand systems in an abstract way. For example, when we are going to consider a system, we are saying that a system or a certain trajectory of a system is stable. What do we mean by stability? And there are very different. There are many notions of stability, and they are different from each other. Each one has its own peculiarities, and so when we talk about stability of a system, I'd like you to be able to apply these different notions of stability to every possible system that you might encounter. Also, if we understand everything in a more abstract way, we might be able to find, and we'd find that we can study the properties of a system using the same tools. So the same tools are applicable to using precisely the same framework, and you don't need to have specialized knowledge about each individual system. Of course, a specialized knowledge about a system will allow you to understand the system better if you have to implement practically a certain control policy or control algorithm. But what is the right kind of control that you need to use, that can be derived using a single framework that holds for all systems. And the third part is the actual practical part. I want you to be able to design a controller so that you can obtain from a system your desired behavior. So if the problem was to understand if a system is stable or not, studying its properties, and the system happens not to be stable, then what is the kind of controller that you need to design so that the system is going to be stable? So you need to be able to understand systems in a more abstract way. If you do so, you'll have a set of tools that allows you to study the properties of systems using this unified framework, and also you can design controllers using this very same framework. So this knowledge becomes applicable to many areas. So these are the goals of this course. So if we want to understand things in more abstract terms, then the language that we are going to use needs to be a very flexible language, and we are going to use the language of mathematics. Since a system is, generically speaking, an entity, the configuration of which changes over time, then we need to have some mathematical tools capable of representing how these changes occur in a way that we can, in a quantitative way. So we're going to consider, for example, differential equations, mostly in this class, but that's not the only option. We could have difference equations, also known as recurrence equations, or more sophisticated mathematical tools that are based on operators and maps that we are probably not going to see in this class. This class will mostly focus on differential equations. So for us, a system is going to be something that can be mathematically represented using a differential equation. And also in control theory, we tend to have this tendency to divide signals into causes and effects. Causes are typically the inputs, the effects are typically the outputs, so we need to have this classification clear. And sometimes it is not, but in most applications it is, because it's clear what is the signal that we can manipulate, and it is clear what is the kind of behavior that we'd like to have. So just to give you an idea that we can use differential equations to model a wide variety of systems. Well, I'll give you just a standard example. You know pretty well that we can model an RLC circuit using a second order differential equation. By second order differential equation, I mean a differential equation where we have derivatives up to the second order. If we just use some relations among components of this circuit, we know that the current running in that circuit needs to be equal to the capacity times the derivative of the voltage that is on the capacitor. That's a fundamental relationship that we know about capacitors. And at the same time, we know that we need to have that if we call U the voltage that is generated by the voltage generator, then this U needs to be equal to this difference in voltage needs to be equal to the voltage on the resistor that is given by the resistance times I plus the voltage that is on the capacitor plus the voltage that is on the inductor, and that is given by the inductance L times the derivative of I with respect to t, where I is the current flowing through the inductor. So if we plug the first equation into the second, we find that the derivative of I with respect to t is c times the second derivative of v with respect to time, and we get a single differential equation where we can assume that our voltage generator is our input, and for example in this case the voltage on the capacitor is our desired output. So in this case U is going to be our input and V is going to be our output. If we have this mathematical representation, now we can start thinking of designing a certain profile for the voltage generated by the generator, so that we have on our capacitor C, we have the desired voltage V. So as you can see, this is a very, very simple way to obtain a mathematical representation once certain fundamental principles are known. Another thing that we can model using differential equations, believe me or not, is populations. And we can approximate, even though the population is discrete, we can approximate that using a continuous variable. There is a very famous population model, that is the Malthusian model, that is tells us that the derivative with respect to time of the population, the increase of the population over time, is proportional to the current size of the population, where the proportional constant is this A that is strictly positive. So when A is strictly positive, I think that everybody can solve this differential equation. We know that x of t is given by the population at time 0 times the exponential of at, and so we obtain an exponential that represents how this population is going to evolve with time. Well, we can plot, we could plot this exponential, but the interesting thing is, can this model be applied to actual populations? And in the graph here I have just reported the world population, so it seems that at least the human population is going up according to something that might look like an exponential. So at least this model, as simple as it is, because it's based on a single parameter A, can at least try to capture some features of some population dynamics. This model is, of course, is not perfect, and it has been improved upon. So I give you this quote for today, that is one of my favorite quotes. Anyone who believes exponential growth can go on forever in a finite world is either a madman or an economist. And this quote is by Kenneth Boulding, an economist. And what this means is that if we have finite resources, we cannot expect an exponential growth. So under the assumption that our planet has finite resources, as it's most likely, then this model is not going to work forever. And there is actually an improvement on this model. We have added a second term. It's a quadratic term, so now our equation becomes x dot equal to ax minus bx squared. This term in x squared represents a form of competition for finite resources among the agents in the population. The probability that two agents are in the same location competing for the same resource in that spot in our finite world is going to be proportional to their squared. So if you have very few, if the population is small, so if x is small, this probability is going to be very small, but then we expect to increase quadratically. So our equation becomes x dot equal to ax is the Malthusian term, minus the competition term that is given by a minus bx squared. The minus is motivated by the fact that the population is going to grow less if there is competition, hence minus, and the amount of competition is modulated by this parameter b. Now if you see, when x is very small, x squared is negligible compared to x, so this behaves more or less like the Malthusian model that we have seen before. And in this graph, where I have solved this differential equation for different initial conditions, if we start with a small population, we see, at least for some time, a certain growth. Instead, if we start already with a very high population, the term x squared dominates the term in x, so this derivative is negative, and so we start seeing a decrease in the population. An interesting part is that when this population cannot increase forever, even when we start small, because at a certain point this term bx squared becomes comparable to ax, and they tend to settle to a certain equilibrium population. And so this is what is predicted by this more realistic, even though not completely realistic, but more realistic model for population. So as you can see, we can use differential equations for a wide range of applications. We can use them for technological devices, to model ecosystems, as I mentioned before, chemical reactions. We can model power systems. We can model the environment. We can model the evolution of temperature in areas, meteorological applications, and so on. So math is not the only tool that we are going to use. I'm assuming that you are familiar with some software or programming languages, mostly for computation and for simulation. Now, I assume that most of you are familiar with MATLAB or with its free clone Octave. That's what I'm going to use in this class, but if you're familiar with other tools such as Scilab or Mathematica or Maxima, that is a free symbolic computational tool, then you can actually use them. So it's not mandatory that you use MATLAB, even though I think that for what we are going to see in the class, it's going to be the most convenient tool. For simulation, we are going to use in this class Simulink, that is part of the MATLAB products. So we are going to use Simulink because it has a nice interface with MATLAB. Otherwise, if you prefer to use, for example, Scilab, there is an equivalent tool that is called Psychos, and so you can use Psychos because it has a very nice interface with Scilab. And Scilab and Psychos are both free for personal use. So long as you're not using them in your company to have profit, if you're not making any profit, Scilab and Psychos are free of use. So that's what we are going to see in terms of programming languages. If you're not fully familiar with MATLAB and Simulink, don't worry. I'm going to spend at least 1 or 2 classes where I'm going to make sure that we are all on the same page. And now let's see what the syllabus of the class is. This is mostly a tentative syllabus, even though I think that I'm quite confident I can cover all these topics. These are not all the topics. There is another page coming after this, but we have started with the introduction, some applications. I hope that I have been convincing enough. And now you actually believe that control systems have many applications, and these applications are fundamental. We are going to spend a bit of time about mathematical models and simulations. I'll show you how to use Simulink, and then we start using our simple mathematical models at the beginning. So we are going to consider first-order systems. These are systems defined by differential equations of the first order, so we only have derivatives up to the first in our differential equation. Then we'll move to second-order systems, and second-order systems are actually more complex than first-order systems. They are capable of more complex dynamics. We start seeing, for example, that in second-order systems we can definitely see oscillations. And then we'll start using some tools to deal with, I'll introduce some tools to deal with higher order systems, that is the generic case. So I'll introduce the Laplace transform. Again, if you have seen it before, that's excellent. If you haven't seen it, I'll spend one lecture to make sure that everybody is on the same page. And the Laplace transform will allow us to deal with higher order systems. To be honest, in this class we'll almost exclusively consider linear systems. I'll define what I mean by linear in the class, but this is a class of systems for which actually that we can solve. What I mean by solve, if your differential equation is linear, then we have actually a way to find a solution of the differential equation. If the differential equation has some nonlinear terms, so if it is nonlinear, then in general we don't have any ways to find analytical solutions to that differential equation, and then we'll need to solve that numerically using some tools such as Simulink. But mostly in this class we are going to see linear systems. So if we are dealing with linear systems, then these two concepts of impulse response and transfer function will play a fundamental role. I'll introduce a notion of stability that goes under the name of bounded input, bounded output stability. Roughly speaking, means that if your input is not large, is within certain bounds, then your output is not going to go to diverge or go to infinity. It's going to be bounded as well. I gave you some criteria for stability. One of these criteria is the Routh-Hurwitz criterion for stability. Then I'll use some graphical methods so that we can start analyzing the system. These graphical methods that are very, very traditional. They're a little old school, I'd say, but still they give us a lot of intuition and some insight, are the Bode plot, the root locus, the Nyquist plot that goes with the Nyquist criterion. So these are methods that are pretty old. They're several decades old, but they were used and created when we didn't have computational resources that were as powerful as the ones we had today. So it was better to use some graphical tools to understand how a system works, because that was more practical. Now that we can put everything in a computer and simulate it, we have faster, better, more powerful ways of doing things, but the insight that you gain from these techniques is still valuable. Sometimes there's certain insights that you can gain that you might not get so easily from a simulation. Then we'll use some ways to quantify stability. These ways, these quantitative metrics are given by the phase margin and the gain margin. And then we'll start moving towards this last part of the class where we start actually designing controllers. And so the first thing that we need to learn is how to track a certain reference point or track a certain trajectory, and so we'll talk about asymptotic steady-state tracking. And then we'll start designing controllers, assuming that our system behaves more or less like a second-order system, because this allows us to have some quick ways to design a controller if the approximation is good enough, and then we'll extend this to higher order systems. We'll see also some kind of controllers, the PD, PI, and PID controllers. The PD stands for proportional and derivative, PI stands for proportional and integral, and PID is just the combination of these two, proportional, integral, and derivative controllers. So these are controllers made of 2 parts, or in the PID made of 3 parts, allowing us to stabilize a system using some principles, some guiding principles. And then we'll use another technique. We'll see another form of controllers, in my opinion not too different from the PID, PI controllers, that is given by the use of lead-lag controllers. And this pretty much, with the use of these traditional forms of control, will conclude the class. So you'll be able to design controllers, at least for some simple classes of systems, or even if the systems are complex, so long as you can approximate them well enough with a simpler system, you'll be able to apply all these techniques. And I have a recommended book, that is the Goloraghi, Automatic Control Systems. I really don't care what edition you're going to use. The content is going to be similar. So if the book is not required, is only recommended. So in case you want to read from a book about the topics that we are covering in the class, that's the book I recommend. I think there are other books that I might recommend, but I didn't want to make your life too difficult to make a choice, so I've just chosen this. Maybe you can borrow it from the library, see what it looks like, and if you don't like it for some reasons, you can actually contact me and ask me, this book is too mathematical or not mathematical enough, so could you please recommend a book that suits my taste better? I'll be happy to do so. I think that this operates a good compromise between being rigorous and also simple enough, making the concepts simple enough so that you can understand them quickly, or making them not more difficult than they should be. And last but not least, the structure of this course. So as you know, unless even if you have lived under a rock, you know that these are a bit of unusual times, and so that's the reason why this class is going to be fully online. Unfortunately, I prefer, of course, human interaction, but that's what we are going to do, at least in this semester. We are going to have online classes. So the approach that I have chosen is this. I'm going to post these lecture videos, this being the one of these, on Canvas. I'm going to post them around 1 p.m. more or less. It might be 1:30 p.m. or so, or even 2 p.m. But I'll try to stick to the schedule. So expect that on Monday, Wednesday, and Friday there is a new set of lecture videos. At the same time, I'll be available online during the scheduled class time, because this class is actually scheduled from 1:30 to 2:15 on Monday, Wednesday, and Friday. So I'll be available online, and you can find me at this Zoom link. So what I would expect from you is just to download these lecture videos, watch them carefully, take notes if you feel so inclined, and so on. Watch them, and if you have any problem and so on, I'm online at this time, and we can talk about the current class, but since I'm posting that at 1 p.m., I don't expect you to have seen the whole class, but maybe we can talk, you can ask me questions about the previous class, and don't feel compelled to watch the class as soon as it gets posted. You can watch that at your own convenience. And of course, these classes, I release them, they are in the public domain, in the sense that I don't mind if you share them, if you save them, if you keep them. I'd be happy if you do so. For office hours, since you can ask me questions from 1:30 till 2:15 on Monday, Wednesday, and Friday, then office hours are mostly if you have to ask me something specific, or something that is more personal. If you have some specific issues that we need to take care of, I'll be happy. Just send me an email and we can schedule time for office hours. Instead, if you want to ask me something and you ask me this at the Zoom link, assume that many other people might be in the same room, and so this is mostly to ask me about technical questions, or if something is not clear about homework assignments. The questions are going to be public, even though I'm not recording our meetings on Zoom. Assume that other people will be able to hear your question and hear my answer. That since this class has about 80 enrolled students, at least at the moment when I'm recording this class, many of you might have the same questions, so it makes my life and your life easier, I think, if I answer the same questions all at once. If there are certain things that are important that are being discussed, for example, some of you finds a typo in the homework assignments and so on, of course I'm going to post an announcement and I'm going to make this available to everybody, even students who were not present on Zoom at the time. About grading, I am planning about 6 homework assignments. Each one of the homework assignments is going to be about 10% of the grade. There's going to be a midterm exam. The midterm exam, I decided that it's going to be on October 19 in the afternoon. The way the midterm exam works is that I'm going to post the exam at noon, 12:01 p.m., and you have to finish that by the end of the day. So it's a sort of take-home exam where you have a little less than 12 hours to solve and post the problems. You are going to post the problems on Canvas using a PDF. So you're going to have plenty of time. I know that some of you have conflicts with other classes. So since all the lectures are available asynchronously, and also the exam you have a window of 12 hours to solve the problems, I assume that nobody should have any conflict this day, unless you have decided to travel or you have some events happening that day. In that case, you please contact me. The final exam, of course, has the same policy. I'm going to post things around noon, and they're due before midnight the very same day, and each exam has double weight compared to a homework assignment, even though they're similar in terms of format to homework assignments. So all summed together is going to be around 100%. The reason why there is this about sign is because I might do a little curving if a certain homework assignment ends up being more difficult than I thought or easier than I thought. I might modify this weight slightly, but I'll try to keep this weight the way they are. And for no other, nothing else is required from you. I just expect you to watch the lectures. Sure, don't feel compelled to watch them as soon as they're posted. You can watch them when you want, but I assume that you're not letting a full week pass without you checking these lectures at all, because then it starts becoming difficult for you to catch up. So please try to be on schedule. The fact that everything is asynchronous is simply because I'm trying to to make this accessible to the largest number of students, and I'm trying to be flexible so that you can accommodate this in your schedule, because I know that life happens, and so to have the opportunity of watching a lecture when it's the best time for you is actually something that I assume is going to be valuable. If you have any kind of question, please you can send me an email, and of course the contacts are on Canvas and are also in these slides. For any questions, don't hesitate.